I guess is it time? My clock is not exactly correct, so that's why I'm asking. Is it already 9:10?
It is 10 past.
Okay, then let's start. Shall I start? Okay, so I want to repeat a few things that I ended up with last time. So we still want to look at this second order linear differential equation and briefly get back to this example. So we have a continuous function on the interval I, and then we can actually specify a solution, little y, which is of course has to be twice differentiable, and we can actually write down an explicit formula in terms of an integral, which is written there, and from that formula, it's not totally obvious that y is actually twice differentiable, or that it satisfies. But so I want to indicate briefly the first step in the proof.
But thank you.
What is this? Oh. Okay, so the thing is you write sine of t minus s as sine t cosine s minus cos t sine s, and then you can put sine t and cosine t outside of the integral because the integration is with respect to s, and then you can explicitly differentiate, you know, and you get the first term sine t integral t0 t cosine s h s ds gives you, if you differentiate, cosine t times this integral plus sine t cosine t h t, and the second term gives you the other terms, and then you see that you have a cancellation here. That's exactly the cancellation which you need so that you can differentiate again. And right, so you get for y prime t just a similar expression as for y t, so you can differentiate again. You have, and you will end up with something that you can easily verify satisfies the differential equation. Right. Now, yeah, this just came up before I started. If you want to see what is special about this particular solution, well, it satisfies the initial conditions y of t0 equals 0 and y prime of t0 is also 0, right? For y of t0 from the integral formula there, it's clear that that's 0, and y prime of t0 is also 0 because you plug it in here. Right. Okay, and there is another fact that we need later on, but here we have to assume that h is not just continuous, but twice continuously differentiable. But then you can make a change of variables. You can, or a change of unknown, so to say. Instead of solving for y, you solve for z, which is y plus h, and then the original ODE transforms into this one, which has the same form, but with a different h, or minus h double, which might be. And this sometimes has an advantage. For example, if h is x, right? If h happens to be x here, then h double would be 0. Or if h is x squared, then the h double here would be 2. And so we all take advantage of that. So now I start a new subsection, 5.3. And here we really do start to work in Hardy fields. So solutions of, yeah, maybe I should say a few more things about why we pay particular attention to this linear differential equation. It's simply, well, I already mentioned first and second order linear differential equations are really crucial to understand, but this is one that's rather special, and it's not really that in itself very important. It's just that it helps us to illustrate a phenomenon that happens for the first. This is a simple case where a certain incompatibility arises when you want to extend Hardy fields by solutions of a differential equation. So it's the simplest case where this happens. Another thing that I want to stress is it might be a bit funny in connection with Hardy fields to talk about things involving sines and cosines, right? Because they are oscillating. But in fact, it turns out that that sines and cosines, and more generally complex exponentials, are absolutely crucial to understand Hardy fields, or the kind of phenomena in Hardy fields that we want to understand. So this is not an accident. Okay. So notation. I want to notation and terminology. I want to. A will be a real number, and then I want to abbreviate. I want to introduce an abbreviation, or CR. This is simply CR A comma plus infinity, right? In other words, the R times continuously differentiable function on this half line. Note that I include A because I want my function to be to have a value at A. My function, right? And oh yeah, and of course for R is 0, we just say CA, CA. And okay, now we also want to integrate up to infinity, so call such a function G and CA integrable. Well, I think let's say integrable at plus infinity. If, well, I don't know if this is standard terminology, but I want, if I integrate from A to T, and T goes, and I let I let this go to T go to infinity, I want this to have a limit, exists in the real numbers. And right, okay, and yeah, I want to also, in connection with this, I sometimes want to, oh, and in that case, yeah, exists in R, and in that case, and then this limit is denoted by the integral from A to plus infinity of GS ds is this limit. plus infinity GSDS, right? So this will be, but I also sometimes want to write this as also for such G, if it's integrable, I want to be able to use this notation, the integral from plus infinity to t of GSDS, which is then minus the integral from t to plus infinity. Right? I want to think of plus infinity as the starting point rather than the end point, but it's just defined this way.
No,
Yes?
little thing. Your definition of integral from a plus infinity is the limit when t goes to infinity to the integral of from a to t, and not a plus infinity.
Oh, yeah.
Yeah.
Sorry, thanks. Okay, right. I want to use this notation. So, right. Of course, this is this makes sense now for every t in the interval from a to t greater than to a. Because of course, if this integral, right, if this integral exists, if you integrate from a to plus infinity, then it also exists if you integrate from t to plus infinity for any t. Okay. Yeah, another thing is I want to extend the usual asymptotic relations on germs to actual functions. So we also extend the binary asymptotic relations to CA, right? In other words, if I have two elements here, F and G, F is dominated by G, meaning the germ of F is dominated by the germ of G. We are always just interested in the end behavior. Right. And now I can state a lemma. 531. Okay, suppose you have a twice differentiable, continuously differentiable germ H, and its germ is Hardian, and yeah, okay. When I say H is Hardian, I really mean, of course, the germ of H is Hardian. In other words, it lives in some. It's an element of some Hardy field. It doesn't matter which one for the moment. And it's infinitesimal, right? H, that means ht goes to 0 as t goes to plus infinity. Then the functions, first of all, then the functions sine s, hs, and cosine s, hs on a plus infinity are integrable, are integrable, yeah. I mean, it's kind of sort of plausible, right? H goes to 0. Of course, sine and cosine are regularly oscillating, but then if you integrate from a to plus infinity, you can sort of. It is very plausible that somehow the limit exists because you have a lot of cancellation where sine is positive versus the next interval where it's negative, and so on. And then the function f and f in C2a given by the usual integration. Ft is the integral from a to, no, now, you see, that's, I integrate from plus infinity to t in order to get something that goes to 0 as t goes to infinity. Sine t. So this is just like the original formula for the solution, but instead of integrating from t0 to t, I integrate from plus infinity to t. And the reason for doing that is that I want f to be infinitesimal, or f strictly dominated by 1. So this is the unique solution, the unique solution in C2a of y double plus y equals h and y, yeah, so it's a solution which satisfies, so to say, this initial condition. Right. Okay. So that's the statement of the lemma. And the proof. Yeah. Okay. So the reason for writing it this way is that if t is very large, then this is, of course, then you expect, first of all, if this integral exists at all, then if t is very large, ft has to be very small. Yeah, because the integral existing means that this, okay. So first of all, h. Now we are, since h is Hardian, we have h strictly dominated 1, strictly dominated by log x. Yeah, so we go to a bigger Hardy field where you have both x and log x, which you can always do. So by the usual asymptotic rules for differentiating things, you get h is log x prime is 1 over x. So h prime is also infinitesimal, but even strictly dominated by 1 over x. And so it's double, and now you differentiate again this asymptotic relation. H double is then 1 over x squared, strictly dominated by 1 over x squared, and so H double is very small. Let t, okay, let's fix two numbers greater than or equal to a. Think of t0 as fixed and t as variable. And then we integrate twice, partially integrating twice. So here we go, integral from t0 to t sine s sine s h s ds is, well, sine is the derivative of minus cosine. So by partially integrating, you get minus cosine t ht plus the integral t0 and t, and then you replace h by, and then you get cosine s h prime s ds. Okay. So so let's oh, sorry, I have to put here, of course, the bounds. Partially integrating. So writing this out, we get cosine t0 ht0 minus cosine plus. Well, wait a minute. What am I? Minus no. Yes. Minus cosine t ht. That's what this is. And then and yeah, and now we integrate this again partially. So we get plus sine s h prime s between the bounds t0 and t minus the integral t0 to t sine s h double s ds which is cosine t0 ht0 minus cosine t ht and here we get sine sine t h prime t, so sine t h prime t minus sine t0 h prime t0 and then again this integral minus the integral from t0 to t sine s h double s ds. Right. Okay. Yeah. But we show that h double is strictly dominated by 1 over x squared. So from that it is obvious that this function here is okay. No, let me follow my notes. So as t goes to plus infinity, sine t h prime t goes to 0. Sine t h prime t goes to 0, right? Because h prime is strictly dominated by 1 over x, and sine is bounded, right? Oh, and this, of course, also. Yeah, I should have. Let me. No, wait a minute. Yeah, this h is also infinitesimal, so this goes to 0 as well. I should have mentioned that first. ht goes to 0, and this integral goes to a constant. Yeah, and integral t0 to t sine s. I mean, this is integrable as a function of s. So this goes to a constant in R. H double is so small. And that means what we have shown now is that this is integrable. Yeah? Therefore, sine s, hs integrable. Since if you let t goes to infinity, all the terms here go to 0 and this goes to a constant. And likewise, you show that yeah, likewise, you show cosine s hs integrable as a right. Okay. Let me see now. Okay. this was really needed to show that, you see, once you know this, you can then use that to show that this is indeed a solution of y double plus y is a. Yeah. So then use this to show f satisfies y double plus y equals h. Let me say, maybe I should just write this, f double plus f is h, right? I mean, this is proved now by the same arguments as we did it when instead of plus infinity as the lower bound, we have t0 as the lower bound. You can just do the same manipulations because these integrals behave just like in the computations that we did there. Okay, and now right, but also f double. Sorry, also f is right because this integral exists. That means if t becomes very large, ft goes. This integral becomes very small. So ft goes to 0 as t goes to infinity. Right. Oh, and now, yeah, we still have to do uniqueness. So this gives you that we do have a solution of this system. Uniqueness. Well, the uniqueness is pretty easy because if you have another solution, it must be simply a linear combination of sine and cosine, right? And another solution differs from this solution by something that is a solution of the homogeneous equation y double plus y is 0. So it's a periodic function, and so it cannot go to 0. If it's a periodic function that is not identically 0, it doesn't go to 0 at all. Uniqueness use that the solutions of y double plus y is 0 do not go, are periodic. Yeah, okay. I think that's clear. Yes. Explain why f. Oh, this one. Well, okay. Okay. So using this integrability that we proved here, this integral does, if you, maybe I should write it out the same way as I did there. Namely, this is the integral of sine t integral plus infinity to t. What is it? I write exactly this, but with plus infinity instead of t0. Cosine s hs ds minus cosine t integral plus infinity to t. What is it? Sine shs. Okay, now, okay, this remains bounded. Sine t and cosine t remains between -1 and 1, But this integral goes to 0 as t goes to infinity. Well, because the limit, how shall I say that? If you think of it as, the convention is that this is really another notation for minus the integral from t to plus infinity of cosine s hs ds. This, since the limit exists, yeah, since the limit exists as t goes to plus infinity, if t is very large, let me see, how shall I explain that? It's if you have a sequence that goes to 0, then the difference between the nth term and the m term for very large n and m also goes to 0. Wait, no, sorry. If a sequence goes to some limit, yeah, then by the Cauchy, the differences go to 0. Yeah, that's the point. If something has a limit, then the difference goes to 0. Finally, yeah. If something has a finite limit, then the difference goes to 0. That's how you should remember it. Okay, so 532, the next lemma. So the same assumptions as before, the same assumptions. As in 5.3, as in 531. Right, so and now the what we want to show is that that then the sign of f is the same as the sign of h ultimately. Yeah? Then sign of ft equals the sign of ht eventually. Lemma. Proof. Okay, well, first, if h is 0, then f is also 0. And of course, then it's true, right? Clear for h is 0, because then h, or maybe I shouldn't say h is 0, h is eventually 0. Clear if ht is 0 eventually, because then f will, yeah, if h is eventually 0, then for big enough t, this will also be 0. Right. So suppose that this is not the case, then, but since h is in a Hardy field, the germ, let me see, where am I? Assume, let's say we do the case that h is positive in the Hardy field in which it lies, right? Or in any Hardy field in which it lies. Then what we want to show is that f of t is also positive eventually. Right. So first of all, we can always increase a, increasing a, the starting point, so to say. We arrange that h is strictly decreasing. Right. Remember, h is infinitesimal, and if it's positive, well, if you think about elements in a Hardy field, if it goes to 0 and it's positive, then it has to go to 0 in a decreasing way. So the range that H is eventually, well, strictly decreasing on the whole interval. Strictly decreasing on a comma plus infinity. Yeah, yeah. We can always change a in these arguments. The germ doesn't change, and notion of integrability doesn't really change if you increase a. Of course, you always then restrict the functions to the smaller interval. Right. And okay, and now then for t greater than equal to a, we split up the integral into infinitely many pieces. Ft equals the integral from t to plus infinity oh, here, yeah, here it's written as an integral from plus infinity to t. You can also write this integral from t to plus infinity, but then you have to, then c times t minus s changes into c sine s minus t, right? So in order to sine s minus t instead of t minus s, h s ds. And now we write this as, we change the board. Instead of integrating from t to plus infinity, we integrate from 0 to plus infinity by, okay, if t, yeah, if s starts at t, then you start with s minus t will be 0. So, okay, so this is the same as sine s h s plus t, yes. And now we split it up into infinitely many pieces into the sum from n is 0 up to infinity of the integral from 2n pi to 2n plus 1 pi sine s h s plus t ds, which oh, I guess this is still acceptable, is the okay. Oh yeah, no. Let me start on a new blackboard. Right, and now we are going to look at this piece. The integral, and each of these pieces will turn out to be positive. If you I could actually no. Is that blackboard also movable, or is it? No. Oh, okay. So that I can't read it. Are there people who actually write on that? Right. So where right. So the integral of the nth piece 2n pi to n plus 1 pi sine s h s plus h of s plus t ds. Well, if you just think about it, you will see that this has to be positive. The reason is, okay, if you let s go from 2n pi to 2n plus 1 pi, then the sign, it starts positively, and then it dips, and then it has this negative part. But h is throughout positive, right? So so if you split it up into the integral from 2n pi to 2n plus 1, well, 2n pi plus pi, you get something positive, and then the second part will be negative, but it will not be so negative that it will cancel out the positive part, because h is strictly decreasing. That's the point. Yeah. So I could write it out, but I think if you just think about it, this will be clear. Yeah. So you're exploiting that h is strictly decreasing and positive. Okay, and then since this is true for every n, you get that ft. Therefore, ft greater than 0. Right, and of course, if f is if h happens to be, so this takes care of the case where h is positive. If h is negative in the Hardy field, then of course, well, the same argument works, or you can change, make a change of variables, reduce it to that case. It doesn't matter, right? Yes, and now a something that I will call a proposition, because it's already somewhat in the direction of the ultimate theorem that we want to prove, 533 proposition. It's a Hardy field. And H is dominated by some finite power of x. Yeah? N is always a natural number in my universe. Some n. So then you have a unique. Then there is a unique y in C2 such that it solves the equation y double right, y double plus y is h. Of course, we are now looking at solutions that are germs. So that simply means that this is ultimately y double t plus yt is ht eventually. And it is the difference with any element in H is non-oscillating. Non-oscillating. Non-oscillating for all f H. And then by the theorem that we proved, this means that it generates a Hardy field over capital H. Yeah. Therefore, therefore y generates a Hardy field over H by the theorem of last time, theorem 513. I mean, there we considered more generally y double equals some semi-algebraic function of y, semi-algebraic over H, so to say, but this is a very special situation of that form. Right. And okay, proof. Oh yeah, I shouldn't go to. Oof. Well, here we do this as yeah, did I or yes. I'm going to use these additive changes of variables that I effect needed later. Well, that's I'm needing it now. So by translation like that, you transform this into that. And the point is that if h is bounded by x to the n, then some sufficiently high derivative of h is infinitesimal. Right? So if h is bounded by or not bound dominated by x to the power n, then by taking, if you take a sufficiently the m derivative of h, yeah, every time you take a derivative, the n goes down by 1 till you reach n is 0. So hm is infinitesimal for m greater than or equal to n plus 1. Right. So so if you now every time you take, so here you can change h to the second derivative. So if you do that a finite number of times, you change your equation into one where the right hand side is infinitesimal. Yeah. So by finitely many additive changes as in um, as in 524 we reduce to the case reduce to or rearrange h infinitesimal. Yeah, right. I mean, these additive, let me see. Yeah, you always change the new z, the new y, so to say, which is z, always differs from the original one by an element in capital H. So the non-oscillation property that you require there is not violated when you do this. So right. And then oh well, wait a minute. Yeah, you're right. Yes. So then the previous lemma, previous 532, yes, gives indeed a y which is infinitesimal in C2 such that y double plus y equals h. And I now want to show that this y will have the required property. Y double, sorry, y minus f is non-oscillating for all f in h. All f in h. Right. And so, and of course you could, and then you can check that this is harmless. You can always, you could say, well, right, but this is not the y that you want. You want because you have changed. You have to make these additive changes, but you can check very easily because the changes are only by things in capital H that doesn't make any difference. So this will do the job. Yeah, this enough. Yeah, will enough. Okay. And right. What am I? Okay, suppose towards a contradiction that it does oscillate, that some, right, suppose it, you have an F where it does oscillate. Let me, oh, I'm almost out of time, but I can easily, okay, let me just finish this towards a contradiction. Suppose F in H and F minus Y does oscillate. Then F must be infinitesimal. F because let me see, Y is right. Y is infinitesimal, and if F minus Y oscillates, that means that Ft equals Yt for arbitrarily large t. So F must then also be infinitesimal. Right. And so for Z equals Y minus F, Z double plus Z equals, well, you can easily check that then you have this is G, where G equals H minus F double plus F, which is still in H, and Z will still be infinitesimal, and G will be infinitesimal, right? Yeah, everything here is infinitesimal, and right. But the uniqueness, now we use the uniqueness in 531 for the H, for G instead of H, and we get that Z must be, yeah, this integral, hence by uniqueness. Yes. In 531, ZT integral from plus infinity to t of sine t, t minus s, gs ds. Eventually at least. Let me see. Unique. Well, anyway, this is enough. And and that means that the sine, so sine of zt equals the sine of gt eventually, right? By I guess by this here. And now we get a contradiction because z is supposed to be oscillating, so its sign changes all the time, while the sign of g does not oscillate, does not change, but is eventually constant because it's an element of H. Contradiction. So that's that's the proof. Okay, I better stop because I'm already over time. And we have a seminar also here?
Not today.
Oh, not today. Oh, okay. Well, then I can answer questions if there are. Maybe I went a little faster here, but it should be. Okay, yeah, good. Good. Mhm. So, was it easy to well, to record this? Oh, yeah. Well, I don't know. It seems a lot of blackboards.
That I've seen use almost all blackboards.
Okay.
Give a round of applause for the speaker real quick.
Oh well.
Sure,
I'm
why
not-
not? Why not?
I'm not. I'm not sure that's necessary because we do it by seminars, not at courses, right? But, okay.
Whatever.
Okay. Good.
Before you do it, the microphone.
Oh yeah, yeah. Of course.
I got it. Thank you.
Right now, I'm supposed to put this thing on again.